Okay. Hello, hello, hello. Okay, so this is Junichiro Horikawa. Hopefully this is on live. Is it? Okay, so this is Junichiro Horikawa, and this is the tutorial live stream for Houdini. And this is the 96th episode for Houdini Algorithmic Live, and the topic for today is to create rather simple Vellum-based system to morph between two objects. In this case, a particle clouds of character A to character B, using simple constraints for Vellum together with some pop forces inside a Vellum solver. Okay, and the result looks like this, like that. Okay. So before I start, I'm gonna give you the brief description how this thing is working. First of all, I am going to create two sets of particles from input geometries. One is A, one is B, using the same number of particles. Then I'm gonna use the Vellum constraints with the type of grains to convert these points into a Vellum grains, so that you can use a Vellum system to create a particle simulations inside a Vellum solver. Then for target B, I'm going to fix its positions to make it as a target, to make it as a final target. And then I'm going to create a stitch constraint, in this case a glue constraint, using this glue constraint type, to connect the particles for the source points together to make it look like the points are moving in like a swarm, like corresponding to the neighbor points moving to the similar directions. Okay, as well as I'm also going to create the constraints between A and B using the same glue but with different constraint stiffness, something like this. Then inside a Vellum solver, I'm going to change this stiffness over time to together with the pop wind force to control the morphing effects. And that's all about it. So it's pretty simple as a setup. Okay, so enough with the explanation, and I'm gonna try to do this from scratch. All right. So, and let me know if you have any questions during the live stream. I would like to make it fast for tonight. Okay, so first I'm going to create a geometry node. Then, first thing first, I would like to have two geometries to morph from morph from 1 to A, 1 to 2, source to target. So in this example, I'm going to use the font, but doesn't really restrict it to a font geometry, but it could be any kind of geometry. Okay, let's type A, and I'm gonna change the font to something interesting. Let's see what I have. Okay, probably this one, brush script MT. Let's choose that one. Brush script t. Okay, so let's give a morphing from A to B as an example. Later on, maybe I can change this to something else to see if it still works. Alright, now in order to create a bunch of points from these characters, I am going to make it as three-dimensional geometry by creating a thickness, applying some thickness using poly extrude. With a bunch of width, maybe that's too much. Yeah, like that. And let's copy this to create the thickness for the target as well. Now I have to close the back side. Alright. Now I'm going to, in order to place a bunch of points inside this geometry, I'm going to convert this into a volume using iso offset. Probably I can copy this value here to this one. And let's make the volume resolutions rather high, like 100. Same for this one. Then use the scatter node to create a bunch of points. Let's test out with the low number of points, small number of points, like 10,000. Okay, do the same for target geometry, using the same number for a point numbers. Alright. So what I want to do is to move each of the points inside the source target, source geometry, in this case A, character A, and make these points go to a corresponding point position to B. Now if you make it a linear movement, it's just a simple morphing which doesn't really look interesting at all. So what I want to do is to introduce some dynamic forces like a wind. So that's the reason I'm gonna use Vellum for this tutorial. Alright, now that I have points, next thing I want to do is to apply same attributes for points inside A and points inside B, so that you know which points should be connected to which points on targets. So well, what you can do is just apply some integer attributes to each of the points based from the point numbers, I guess. So, or it could be random. Let's see if the point order is some rules. I think these are random, so I'm just gonna pass the point number as a integer attribute. Now the name could be anything, so let's name this cluster. I'm gonna create the integer attribute cluster derived from ptnum for both of them. So if you share the same cluster ID, cluster numbers, then that's the goal. That's the target point you want to connect from A to B. Alright, thank you for the comment, everybody. Oops. Let me also save this. So this is 96th episode. Particle. Right. Now I am ready to create a Vellum constraints or Vellum geometry. Let's merge these together first. Now I guess in order to know which one's which, it might be a good idea to have a group for points as well. So let's do that for the left hand side, I am going to name this source. And for the right hand side, I'm gonna name this a target. Right. Then merge it together, and I'm gonna use the vellum grains, vellum configure grains, to convert these points into a vellum based grain types. Right. Now I don't really need, in this case, I don't really need like any collisions or self-collide detections or anything. So I am going to, first of all, ignore about this particle size, and also turn off the display as sphere, turn off add sprite material. Just gonna see it as a point itself. Right, and particle size doesn't really matter in this case, but I'm just gonna leave it as it is or make it smaller just in case. All right. Now let's see what I have got from the output. From the first output, let's look at the geometry spreadsheet. I have the point information, point position, plus clusters that I have created. And these are the added additional attributes from this constraints node, such as p scale, mass, is grain, and so on. Okay, let's look at the second one, and the second one doesn't really have anything except for the points, so that's that. Now what I need to do in this case is to make the target points, which is this B, the points from the B geometry, to be fixed in this position, very position. In order to do that, what you need to do is to go back to the point attribute, output it from this vellum constraint grains, and change the mass information. If the mass is equal to 0, then it is not going to be affected by any kind of forces inside a vellum solver. So only for the target points, I'm gonna set the mass to 0. So to do that, I'm gonna use the point wrangle, or you could use attribute creates as well, and change the name to mass target, or target mass, then filter it to target group and change the mass to 0, so that it will be fixed onto this very position. Now let's check. For the target points, the mass becomes 0, so that's good. Okay, at this moment I can already check if this is working or not, so let's create a vellum solver, connect what I have right now from the constraints. Now the second one and third one doesn't really have any info, but anyway, here it goes. And right now I only have a gravity, so let's see what happens with the gravity force. Now, as you can see, only the points from the source geometry has been falling, and B is being fixed at this position, so that's good. Now for this setup, I don't really need a gravity, so let's turn that off. Go to the simulations, no, go to the forces, set the gravity to 0. Also, I don't really need the collisional detections for this setup. I am going to turn off this enable collisions, which will make the simulations faster. Okay. Also, I might not really need to set the constraint iterations to 100. Doesn't really have to have many steps to calculate the constraints, because the constraints that I'm going to create is just a simple 1-to-1 constraints. So I think it is okay to set it as 1, well, or 10. Let's try with 10 and let's see if I can move this to 1 as well, which will make the, again, simulation faster. Now let's go to the cache memory and increase this a little bit, just in case. All right, so that's that. And if I play it, now the points is exploding. It's not around, doesn't really matter about it right now. And what I want to do is to what I am guessing why it is exploding. Maybe it is colliding with the p scale or something. Let me try that out. Let me go back to development constraints grains, and if I set the particle size to really small, what would happen? Okay, so the self collision is still alive, seems. That's not really what I want. Let me check this again. Okay. Okay, so it is alive. Well, probably setting this off don't really make any difference, so let's just give a p scale really small, or just maybe just equal to 0 might be okay, not sure. Nope, let's just make it really small. Yeah, so that it doesn't move in an initial setup. Okay, now next what I want to do is to apply some forces in order to spread the particles from sources, and rather make it interesting, like a swarm, the movement of the swarm of fishes or something. So for that purpose, I'm going to use a pop force, something like pop wind, or let's search for wind. Yeah, pop wind. And let's see what happens with this force. Okay, and if I increase the amplitude a little bit, okay, exploded a little bit too fast. Let's make it a little bit smaller in terms of the amplitude. Okay, rather nice. But as you can see, over time, the particles being spreaded too much doesn't really look like it has some like collective movement. So in order to have something similar to a swarm intelligence movement, I'm going to stick the points together, which is at the neighbors, with some small forces or small constraints using a glue. So let's do that by using a vellum glue. Right, and we can check the connection by looking at the second output. And what I want to do is to connect from between points and points. And I want to only connect the points between the source points. Okay, I don't really need to create any connections between the target. So in order to ignore that, I am going to make this source and this one to source as well. Alright, so not every point is being picked for this setup, so let's increase some of the parameters so that every point will be connected somehow. So let's increase this one. I can see the points is being connected more and more. So each point, this is indicating the number of points which can be connected with each of the point. And probably I could also increase the search distance to something big, maybe 10. And I think 3 isn't enough, so let's increase this a little bit more, like 6. Okay, that looks enough. Let's check. So with this glue, now what I need to do is to set some stiffness, how hard the spring force is in between these points. I don't want to make it too hard because if it's too hard, then it's not going to like fly away with the wind. So let's try with the original setup and see what happens. Now we already create something interesting, but it still have a neighboring connections somehow. But it's looks a bit too much, I think. So let's see what I can do with the setup. First of all, going back to the glue, and first of all, the stiffness can be a little bit smaller, like 1. And I'm not sure if I need a compression stiffness since this is not a cloth. Maybe I don't really need this. Alright, looks a little bit better. Maybe splitting a bit too much. I don't know. Oops. How about making this 5? Maybe a little bit too strong. So let's keep it as 1 for now. See if I need to change this later. And at this point, I think I can increase the number of points for testing. Let's say 30,000. Okay, starting to become a bit interesting, a bit more interesting. Alright, so what we need as a result is to move these blown up points to go to the B position at some point, naturally. Naturally is the point. So how do we do that? In order to do that, we need to have another constraints between A and B, which we have like transparent, invisible connection between the points from source to target, and at some point for a some of the frame, it's not, those constraints is not going to be active, but at some point on the time frame, it'll going to be gradually activated, gradually be strong. The stiffness becomes really strong. Then in the end, the particles will be connected to this B. That's the goal for this setup. So in order to do that, we need to create additional constraints to connect A and B, just like I did with this glue node. Now for that purpose, there are ways to connect I mean, there are ways to create the points between A and B with the which shares the same attributes, but which you can use this option here, but it's gonna take a bit too much time to find the corresponding points using these options, because it's searching for all the points which from the closest points until it meet with this conditions. So instead of doing that, I'm just gonna make it parametrically or procedurally using wrangle to make it faster. Okay, so the number, first of all, the number of constraints that I need, in this case a primitive lines or polylines, which looks like this, is the same as the number of points for source and target. So for this one, the number of particles is being chosen or defined right here. In this case, 30,000. So let's copy this parameter and let's try to make a number of constraints using this information. To do that, let's look at this second output from this vellum glue and see what I can do from here. So if I look at the geometry spreadsheet, for the point attribute, I have actually 60,000 points, which is the combination of the source and target. So I know that the number of points are the division of 2 of this total number of points from this output. And if I look at the primitive, these are the actual constraints that I need to create. And currently these constraints, the already given constraints, are created from this vellum glue. Now what I want to do is to create a similar glue constraints which has this exactly the same attributes like showing here. So you have constraint tag, damping ratio, rest length, original, stiffness, and type. Those are at least the necessary minimum necessary attributes that need to make the polyline as constraints. Anything else I need to add? I don't think so. So let's do that. So in order to do that, I am going to look for a point first of all. Okay. And let's call this target stitch something. And I note that the number of points is being defined on the scatter node. Let's get that information first. Space relative reference, get 30,000. Now, the first 30,000 points from this output should be the source. The points which belongs to source, because I have added in the first as a first input to this merge, and the second input for this merge is the target. So the later 30,000 is the target points. So I know that is the rule here. So if pt num is less than number, then that should be the point which belongs to the source geometry. So from this source geometry, I want to create a primitive. The line connects to the target. In order to do that, I do need to know the target point number, but you can get that by just adding pt num with num. And that should be the target point number, the corresponding target point number. Then you can create the line between those 2 points. using at prim with the polyline connecting pt num and what was it? Target pt. Okay, just like that. Now, in order to make it looks different from the original, I mean the already existing constraints, I'm gonna color this to different colors just to make it visually interesting or for analysis. Like, let's make this red color. Right, so the red lines is the constraints which connects from A to B. Alright, which should be randomly chosen, I think. Now, let's also attach some group to this primitive so that we can get that information later. Let's name this target stitch to line. Alright, what else? I guess that's about it for this. Now, what I want to do next, if I look at the primitive that I've just created, as you can see, the attribute is not being set, something like dumping ratio, rest lengths, rest rank original, and so on. So what I want to do is to first of all copy the existing attributes coming from the second output, which have these informations, to the new target stitch groups by just using attribute transfer. Okay, from primitive to primitive. I'm gonna just copy everything for now. For point, doesn't really matter, so you can uncheck it. And let's see. And for the conditions, I don't want to use the distance, so let's check off this distance threshold so that everything will have some kind of numbers being applied or copied. Now, as you can see, the value has been transferred, but what's not correct here is this rest lengths and rest rank original, because rest lengths has to be the actual length of this line, but it has been copied from the existing glue, so this is totally wrong, so we need to fix that. Other than that, I think it's fine. The stiffness is equal to 1, but those stiffness is going to be control over a vellum solver, so, and as well as maybe the rest lengths as well. We can set the rest lengths to 0 for the final conditions. If it's equal to 0 and if you have some kind of stiffness, meaning point A and the point from the A and point from B is being like connected with no lengths, no 0 lengths spring, meaning A has been transferred to B. So we can start the stiffness from 0, then gradually increase it over time so that at the end it will have more spring to pull each other, and B, since B is being fixed to that position, only A is moving to B, and keep the rest length equal to 0 so that we don't really need to worry about these info. So we only need to gradually change this stiffness procedurally over time inside vellum solver. Okay, so that's the plan. So let's change some of the initial attributes using primitive wrangle. Okay. And let's set the filter to target stitch and best length is equal to 0. Also, let's set the what was it? The stiffness to 0 as well. Okay, as an initial condition. And that's probably it for a initial conditions. We have two types of constraints. One is the target stitch group and one is the constraints which connects the points over A. Now we might also need to know the group for these groups, this white glues. So let's go to the Vellum solver and let's create another group for this white one. It's called a stretch. Just use the stretch as it is. It's fine. Okay. I think everything is ready. And let's connect this to a second input of this Vellum solver. And as a final output, what I want to do is to just show up the source geometry. For the points. Right. Okay, now is the time to change some attributes inside the Vellum solver so that the constraints, the stiffness of this target stitch group glue constraints is going to be activated over time. Okay, let's try that. So going inside and let's use since I want to use a ramp parameter, I want to use the SOP solver. And I'm going to use the second option, this SOP solver constraint geometry, which can control geometry as well as constraints in one network, which is a great setup. So let's use this. So what I want to do, what I want to control here is the constraints. So I'm going to use this network here. Now, if I visualize this, okay, nothing shows up. Let me go back to, okay, gotta connect this. Okay, this will show those second input geometries, which is the constraint geometries like this. And what I want to do is to modify this red line's stiffness over time and see the effect. Over time, I want to increase the stiffness. Currently it's 0, so it's really not working at all. Like that. The length is free to move. So over time, I want to increase the stiffness so that since the rest length is equal to 0, it's going to pull each other more and more over time. So let's do that by creating a primitive wrangle. I'm gonna name this target stitch stiffness, and then first of all, I'm going to get the frame-based value. First of all, divide the frame by frame end, which will give you a value in between 0 to 1 based on this frame number. So from 0 to 1, corresponding to these lengths of current timelines. Okay, and based on that, I am going to feed it inside the chramp parameter. create a curve like this, and I'm gonna make it B-spline and B-spline. I'm gonna try it with the linear setup first. Let's move this a little bit to somewhere around here. Now, the actual things that I want to do is to modify the stiffness of this lead line. So filter the target stitch. And change the stiffness using the frame-based value. And at the end, I want to make the stiffness really big, so you will be assured that the points will be connected with 0 lengths. So I don't know what's the best value here. Let's try with 100. Let's see what happens. Okay, let's see. Going back to the geo. Just visualize A, which I am seeing some caches here. As always, doesn't go away. Okay, how do I get rid of this cache thing? Never get used to this cache thing, and never seems to go off. Help reset viewport. Thanks for the info. Door to nothingness. Help reset viewport. Oh, wow. That was it? Thank you. This is useful. This was great. Okay, then. Now, there's too many bounces and it's going too fast, as you can see. But it is changing from A to B. But the wind force is being lost. The constraints is too strong. Happening too fast. And I don't, first of all, I don't really need this bounciness. So in order to remove this bounciness, what I can do is to first of all go into the vellum solver and try to make the solver constraint iteration to 1. Okay, well, it didn't really solve, but the simulations becomes a bit faster, so that's fine. And what I can do next is go into this glue node and change the dumping ratio to something really high, like 0.3. I'll still have a small bounciness, maybe 0.5. Okay, something still wiggling. Funny, but a lot better, I guess. Okay, so what I want to do next is to control the timing of this stiffness growing. Now the reason why I'm not using vellum constraint property nodes is because of this ramp parameter. I mean, you might be able to use this ramp parameter inside of vellum constraint properties. I don't know, maybe. But I couldn't figure out how, so that's kind of a reason why I'm using subsolver. And probably you could add additional like informations inside this if you need, so which could be really flexible later on. So in terms of the timing, let's change this to something So for a few frames, the first few frames, I don't really want to disturb the wind forces, so keep it as it is for a while, making the stiffness equal to 0, maybe until 50%. Then make the stiffness really high in short amount of time, something like this. How's that? Phew. Now let's see what happens. So for the first few frames, the wind is working, and at some point the stiffness becomes higher. Go to the B. Alright. Now the last wiggling that I'm seeing here, I think is coming from this glue here, which I am not controlling anything. So I think I do need to make the stiffness of this glue to 0 as well, with some kind of timing. Alright, so let's see. Let's see if we can do that. So for that, I am going to create another primitive wrangle. And stretch stiffness. Use the stretch group and change the stiffness over time. Same as I did right here. Or probably I can just copy what I have for this target stitch and use it for stretch. I don't know if I need to set the same numbers, probably not. Okay. So for this one, I don't want to increase the stiffness, but instead I want to make the stiffness equal to 0 over time. Okay. And let's try keeping this timing, this ramp parameter as it is for now, and let's try to make it equal to 0 from the original value. Now at this point I don't really have the original stiffness value inside the attribute, so I think we need to create that beforehand outside development solver. So where could we do that? Maybe somewhere around here. We just need to copy the current stiffness as a additional attribute, which is not going to be changed over time, over dynamic simulations, but can be referred inside a subsolver as a constant value. So I'm gonna name this rest stiffness. Just copying the current stiffness as the initial value for stretch, or maybe I can do both for target. In those cases, maybe I can just put it right here. Alright, now let's go back to the subsolver, and the actual value here is, first of all, rest stiffness, starting from the rest stiffness, then multiply 1 minus f. So f is starting from 0, so this will be resulted into 1 for first few frames, which means you are using the original stiffness for a while. Then it is going to become 0 over time with this timing. Maybe I can shift everything to left a little bit this to 3, 5, 7, 9, like that. I don't know. And let's see. Let's check. Play. Okay. It's not that bad. Maybe timing might be too fast at the end, but this is more or less a way that I would like to tell you today. Yeah, I think I like it. Now probably I could do a little bit more with this wind thing. If I make this to amplitude to 2, that's spreading too much, but it's more interesting. In order to avoid making this spread too much, probably I could go to the element solver itself, decrease the time step a little bit. Yeah. Okay, and after that everything is up to those different values for parameters, such as the stiffness of this glue inside the source. If I make this 10, it will become more collective intelligence or collective swarm-like moveness, which also looks interesting enough. 5. Yeah, I think I like this. Or maybe a little bit more spreadness. 3. Alright, so let's try changing the geometries to something else and see if it's going to still works. In this case, I'm just going to change from one geometry to another geometry. Okay. Car. Well. Looks fine. One thing I didn't try before this streaming is to fading things away gradually, maybe from top to bottom. Maybe I can try that here on live and apply that to this system as a tryout. Okay, let's try that. So in order to do that, what I could do is to create some conditional conditions when to apply the pop force for this geometry. And For that, let me think. I could either use a mass or some constraints again. Yeah. In terms of the wind, I guess I could just use the mass properties for when to blow the wind. I mean, when to blow the points based on the wind. So let's try that. Maybe I can do this inside of Elm Solver. And in order to change the mass over time, I could do this inside here. And let's look at the geometry. What kind of information do I have? Do I have a mass? Yes. So let's try to change this mass over time gradually. So initially everything is 0, so A is not moving at all, but gradually from top to bottom the mass will become 0.1 so that it will be affected by the wind over time. Maybe for first, I don't know, few frames, 60 frames for 2 or 3 seconds. So in total, I'm gonna set it to 400 frames so that I can have a long preview. Now, I'm gonna use the point wrangle in order to control the mass. Alright, and in order to control the mass using some kind of a bounding box, I do need to have a bounding box informations, I think, which I don't really have it right now. So let's have that info applied to maybe to a detail attribute. Maybe you can do that somewhere around here or somewhere around here. Yeah, since I only need those informations to A. Also, in those cases, maybe I can apply the information to the point attribute, which might not be efficient, but is useful. Okay, so what kind of information do I need? Size. Size. Like that. Maybe I can do the same for the target. Alright. Going back to the vellum. Solver. Filter to source. Then gradually change the mass. First of all, let's define how many frames I want to use to gradually change the mass. Let's try with some small number like 40 frames. And let's create a value between 0 to 1 based on the current frame. Divide by frame. And at some point this becomes more than 1, so let's clamp it to maximum equal to 1. Alright, just like that. And now I can change this f to a mass value. Probably making it linear makes sense for this purpose. So starting from f, so initially want to make it 0. And wait a minute. Now what I need is the point position information to gradually change it. Right. So in this case y value, so point y divided by, wait a minute, actually what I needed was not the size information but the minimum and maximum. Minimum and maximum for the bounding box, and that was the information that I needed. Alright, let's delete this and copy this to here. Right. Do I have that information? Yep. Right here. Right. Going back. To this, and the y value, I also want to make it from 0 to 1, which I can do that by fit point y with bounds min dot y bounds max dot y. All right. Now is the time to make a condition. If y is less than f, no, based on y, I want to gradually change the mass value, right? So what's the best way? Initially the mass is 0, right? Starting from 0, and should be something really simple. My mind is not working. Okay, so y is the condition. Okay. Right. And add it by f, or nope. Okay, I'm just gonna make it as a simple conditions here. If y is less than f, then f mass is equal to 0, right? No. 1. Else 0. Yeah. Let's try with this. Well, other way around, but what's happening? It's being fixed. Seems like it has some kind of ceiling. Interesting. And I know why. Gotta do this. Maybe I didn't really need to clamp this after all. Wait, yeah. Okay, well, I don't want to go from top to bottom, so the condition is the other way around. Wait, no. Mistake. So 1 minus y. Right, maybe that was too fast. Let's make it a bit slower, like 90 frames. And maybe the gathering could also be done gradually as well. Probably. I think I'm alright with the effect, but it's a bit too spread out, so I'm gonna modify some of the constraints again for the glue to make it maybe 5. A little bit better. Okay, so let's think about how we do the gathering. I don't think I can use the mask for this one. So instead of using the mask approach, I do need to use the constraint stiffness approach, which should be somewhere this one. Alright, so I just need to change the timing when to apply this stiffness moving. Alright, so let's create another frame when to start gathering. And this will be the offset value, I guess, offset frame value. So probably I could use a similar value like 90. All right, and let's see. I think I need to modify some of the values here. I am assuming that changes is happening. Some of the value is changing really fast based on the point positions right here. So let's get that information first. Y, and I also have the bounding box information. Just like that. And what I can do is to multiply the frame by y, right? So if y is smaller, you'll get 0. If it's y is equal to 1, then you get 90 frame. So that is going to be the offset value. And I want to use that value somehow to this one. Could be a plus value, plus to this one. Then clamp it to 1. Zero to 1. I don't know if this is gonna work. Let's try. Let's see what happens. So the first 90 frames, A is blowing below the way from top to bottom, and somewhere nope, I don't really see a gradual change here. And I also see some wiggling happening a lot. Well, that's probably due to the wind as well. But it's not going from top to bottom, I guess. Somehow it is not really working. Let's see. Okay. That is because I don't have this information from primitive. If I look at the point, well, point doesn't really have that information as well. Okay, yeah. So that's the reason. So I do need to get the bounds information from the point, maybe from this point right here. So I'm gonna connect this to a second. Wait a minute. Yeah, that's fine, I think, because every point shares the should be sharing the same bounding box value. Yep. I just need to make sure that I need to get the target information, target points information from the second input here. So how do we do that? Forgot the function's name. Let's search for it. I think it was called something like expand point group. Yep. To get the point number list shares the same group. Alright, yeah, this could be used. So expand point group from second input. I want to look for the target. That's probably it, right? Yep. And any point which have this target group will have the bounding box information. So I'm just gonna get the first point, then get the bounds min using the point, and bounds max. And replace it with this one. Alright, how's this? Let's see. Let's check if I have got the correct value. Looking at the drum spreadsheet, primitive. Nope. I am not getting. Okay, I do. Actually, I do. For the target stitch, yeah. So that's good. What about the max? Okay, I am getting it. So hopefully this works. Going back, play. It does seem like it started from B. Not really sure. Maybe. Maybe I do need to make it a bit more faster for this transitions from spreading particles to B. And somehow avoid this wiggling thing that's happening here. Not sure what is causing this wiggles. Probably the stiffness isn't big enough, I don't know. Or the wind is a bit too big, wind is too big. But if I increase the stiffness over time, would it change it? What if I make it 500? Let's do it somewhere from here. Okay, looks better. And in terms of the timing, maybe I can increase the frame for offset. 180 frames to make it more gradual. Yeah, it's slowly making B. Okay, that looks cool. Nice. Nicely done. Probably I can also make these first blowing away a bit slower. And also I don't want to really use the if conditions. Instead I want to gradually change the mass. So let's change that as well. Now the thing that I did here could be also used for this one as well. So let's bring this beforehand. And also let's make this 100, I don't know, 30 or 50, 40, never mind. And then what I am going to do is what I also did here, create an offset value by multiplying the offset frame, the maximum offset frame by y, like this. And then add it or subtract to this frame. Now which one should that be? I don't know. Negative in this case. And then clamp it between 0 to 1. Yep. Now I can directly use this f value to a mass value. Starting from 0 to 1. Yeah. Let's see. No. can just change this here, 1 to 0. I guess I need more spreadness, but it is working. Oh, it's moving, changing too fast. Interesting though. Interesting though. I do want to have more spreadness. Let's make this stitch to 4 and maybe 3, and change a little bit of timing for target stiffness. Maybe I'm gonna make it 150 for this one and also 150 for this one. Anything else? Let's make it a bit more sharp. Like that. To have a quick change. Right? Yeah. Pretty natural, I think. Yeah, I think I like it. I think I like, well, although I don't really like how it's been blown. I want to have a bit more dynamic blows, which I don't really have it right now. Maybe the stiffness is a bit too strong. If I change this to 1. Okay, another reason I think I know why is because I realize when I change the mass, I'm using this at P, which changes over time, which I don't really want to use. I want to use the original point positions for this condition. Same for the target. So let's create that original point position. Just going to use rest position node for somewhere here. Yep. Which will copy the original point position as a rest value. Now I can refer to that value. Instead of using point, I'm going to use rest. Same for this one, but I'm not sure if this one has the rest attribute. Nope. So I think I need to refer to that value from this. No, but the point number is the same, 60,000, 60,000, so I can just use the point pt num to just refer to get the rest position. Like that. Okay. Let's see what happens. Better. Better. Yeah, much better. Yeah. Nice. Huh. Okay. Okay, that's it. That's probably it. That's pretty much it for today's tutorial. Let me know if you have any feedback or questions or suggestions or anything or comments. That would be great. And this should work for any kind of input. So you can play it out with this setup for any kind of morphing. Of course, we always like to use pighead, as well as rubber toy. And the simulation is rather fast because I'm not using any collisions here. So that's one good thing about this setup. I think I can increase the number of points here to 50,000. And it still is decently fast. Blowing it away. And it is creating something we already know. Yoshi. What's this? What's this? What's that come from? Ah, because of this extrude. Forget about it. Okay. Okay, thanks for all the comment. Thanks for watching it. As always, I am going to upload this file to a GitHub repository, which I am going to paste the link to the video description page of this YouTube video, so that you can download it and use it for your for anything you want to do. And I am also going to upload the file to the Patreon page, so it will be great if you could also support could be a supporter to continue doing this kind of tutorial. Okay, that's pretty much it for tonight. It is 1 a.m. in Japan time, so I'm gonna end this. And as soon as I end this, I'm going to upload the file so you can download the file to play out with it. Okay, that's it. Hope you find it interesting. And yeah, I found it interesting myself, so that's the most important thing. Yeah, at least I am pretty satisfied with the results, so I hope you do as well. Thank you and good night, and see you sometime next week. Sorry for the random time, as always. Can't really set the constant time recently, so but I will try to make it weekly at least. Okay, good night.